Testing.
Perfect.
That actually has
Hi, Alok. We can see you. Thank you for joining.
Okay, I have to stop my video and
Yeah. Okay. Yeah, I think I'll start. So I welcome one and all for this week's Wednesday colloquium, and we have a distinguished visitor coming all the way from Canada, actually spending some time in India, of course, Professor Arif Babul, who is actually currently a distinguished professor and Infosys visiting chair professor at Indian Institute of Science in Bangalore. Okay. So before I let Shubhadeep introduce Arif, wanted to just tell Professor Babul that this colloquium series is pretty historic for us because it was started by our founding director, Professor Homi Bhabha, and it has allowed for sort of putting all the natural sciences faculty members to mingle and mix while listening to an expert in any area of physics, chemistry, and biology. And that has benefited not only the colleagues, my colleagues as faculty members, but also the students, and has been sort of a very successfully run event. Some of the previous colloquium coordinators are in the audience. And it has been much treasured by us. And so we welcome you for this distinguished series. and I'll let Shubhodip introduce you.
Thank you very much. So at first, let me welcome Professor Arif Babul at TIFR. He's visiting us for almost a week and possibly visiting us soon again. As Jenny just now mentioned, he is a distinguished professor at the University of Victoria, and also visiting chair professor at IISc Bangalore. So the list of his successes and different works is quite long, so I'll be taking a few minutes to tell it. So Arif completed his PhD from Princeton back in 1989, and then followed by a fellowship, the NATO Science Fellowship at Institute of Astronomy in Cambridge. Then after he did a postdoc at CETA, and then he joined as a faculty in NYU, and then with about 3 years over there, he moved to University of Victoria, and since then he was there for almost last 25 years. So he has worked on several different topics. Some of you must have heard his talk on astrophysics, DA seminar on last Friday. So he has worked on topics starting from galaxy formation, AGN, gravitational lensing, cosmic strings, warm dark matter. So depends upon what is your interest, you can always find something to talk to him. And he has worked on both theoretical problems and computational problems, and also on computational neuroscience. So people over here working on biology, may be finding something common to discuss with Arif. He's a foremost authority on the assembly, evolution, and physics of galaxy formation and groups and cluster. One of the main interesting thing I would like to point out, which is only a limited one, is he has been listed as one of the top 5 globally scientists. Recently, he is also a recipient of several prestigious international awards and fellowships, which includes the NATO Science Fellowship, the Kavli Frontier of Science Fellowship, and several others. With no further delay, floor is all yours, Arif.
Thank you.
Thank you so much for visiting us.
Thank you very much. I was warned about the honored tradition of this colloquium, so I pulled out my jacket. It's the first and only time I'm wearing the jacket in India this time around. It is an absolute pleasure to be here. I'm honored to be invited, and I was told that the lecture would have a broad audience. So I have tried to pitch it at that level. I'm also cognizant of the graduate students in the audience. So I will be giving it the talk at the level where it will both give you an insight into what it is that we're doing these days in computational physical astrophysics, and also tell you something about the state of the art and about the opportunities that exist as we look ahead. So the title of the talk refers to knowing the universe, revealing and replicating. I have to back up a little bit and say that, you know, being in this area is sort of challenging. You know, as a physicist, you are used to constructing theories, and as a experimental physicist, you're used to building experiments that would go around, you know, either testing certain phenomenology or testing theories. But the advantage that an experimental physicist has is that they can change the conditions, they can tweak things here and there. We have but one universe, and the experiment started 14 billion years ago, and that's it. That's what we have. We have to make the best of what we have. And so part of the challenge is to try and understand what the universe is, how it started, how it's emerged into the structures that we see in the universe today. That's part of the revealing. And then the question is, as creative theorists playing in the sandbox, we can come up with multiple explanations for any given phenomena. In fact, my supervisor, Jerry Ostreicher, had a famous message for all the graduate students who were training in theory. He says, theorists only have to be right 5% of the time. The experimentalists have to be right 95% of the time. Essentially, the idea was you give us a phenomenon. You point a telescope, see something interesting. As a physicist, we should be able to write 3 different papers on the same thing, and then leave it up to the observers to figure out which one of those theories is right. So That trying to understand that over time obviously became a lot more complicated, but also became a lot more sophisticated. And so I'll tell you a little bit about that. The outline of my talk is essentially as follows. I'll give you a brief contemporary history of the field. At some point, I will reach a junction point where I could either go left or right, and I have chosen to go to astrophysics. When I come back, I can give you a talk on the cosmology part of this path. So that's the path. If you keep walking down the path, it will split. Identifying and modeling the physics of cosmic structure formation is the next part. And then I will finish with a progress and challenges. And so let's get started. When I was in graduate school, the general understanding of the physics that shaped our universe was highly uncertain. Okay. The age of the universe at that time was estimated to be anywhere between 7 and 20 billion years. We knew by this time that the baryons made up a small fraction of the total matter distribution, but how much was sort of uncertain by about a factor of 3, between 5 and 15%. Models of everything, including the large-scale structure, the expansion of the universe, and the formation of galaxies, were, I would like to say, highly imaginative, highly simplified. This is the spherical cow thing that the physicists are famous for, and largely untestable. That's the situation. So when I said earlier that we were basically playing in the sandbox and had everything at our disposal and were completely unconstrained by data, this is like the theorist's paradise. But it does has its challenges. And so things started to change. They started to change in about 1990s. Just as I was graduating from grad school, the situation literally transformed. Digital films, and I mean CCDs, whose maturation astronomers played a very important role in, and the development or the coming online of very powerful telescopes, both ground-based and space-based, transformed our field from being data-starved to what I've written up there, big data, but honestly today, if we think about it, it's data overwhelmed. And in addition to that, powerful new computing devices. So GPUs that could run calculations faster and faster, and computers with thousands of cores, which you can leverage, made it possible not only to analyze this data, but also now start modeling the universe itself. So let me give you a flavor for kind of changes that have happened over that time span. Very first thing, we knew that the galaxies came in different shapes and sizes. We now know that they come in a wider variety of shapes and sizes than previously, thanks to the Hubble Deep Field. We have, where did I put my thing? Yeah, there it is. I got it. So we have galaxies that look like smudges. We have galaxies that have shapes of frisbees or disks with stars organized in a disk-like configuration. We have galaxies that are organized in as spherical balls of stars, and everything and anything in between. This is the full the galaxy zoo. We now have a pretty good idea of what the galaxy zoo is. We have a pretty good idea of how things change from one to the other, and also the subtle differences in the structures we are now able to understand and model. Next, let's zoom out and look at the galaxies as a whole. Now, okay, we have to discount our own galaxy, which is running down the middle here as a band, but every other dot up there represents a galaxy, an extragalactic system, an island universe like our very own. Now, if you look at this image, you see that it looks pretty smooth. The question is it really smooth? And now you can start to play this game. You can measure the distance to these galaxies, and start to group them by their galaxy, by their redshift. So if you do that, you start to notice that there are concentrations. There are these large chains of galaxies that stretch across. You can see that most clearly in this image. In that sense, the local universe, and certainly even the midfield universe, is not homogeneous. It looks pretty much isotropic, but it's not homogeneous. There are large organizations of galaxies in filaments that stretch out hundreds of megaparsecs. We have dense concentrations of galaxies bound together by gravity, numbering 1,000 or 2,000. And we have walls, literally sheet-like structures of galaxies that span across the entire sky. One of the most famous ones is known as the Great Wall of the Northern Sky, or the Northern Wall, or the CFA Wall, which was discovered in mid-1980s by people like John Buchra and Margaret Geller.
Arif, just a quick question. I'm a chemist. I'm completely out of the field, but
Sure.
I would like to know the granularity that you show here. What is the length scale of these clusters, for example?
The length scales of this, something
These
like
things,
yeah. I'll actually give you an idea of that in a second. Just to one of these tight knots is about 3 megaparsecs, so that would be roughly about 10 to the 24 centimeters. So then in itself, they're pretty large. So, as I said, these filaments that you see here, so here's one of your length scales. These filaments that you see here stretch hundreds of millions of light years. And then in addition to that, you can lay out the structure in distance space or in redshift space and look at the structure, and you see that it's not homogeneous. These are walls. It looks like a sponge. You take a sponge and you cut it, this is what it would look like. And in fact, the sponginess of the universe is one of the many ways people try and describe the topology of large-scale structure. So what we have is a universe that looks organized. It's very rich. And one of the questions is, how did it emerge? So that's the next thing that I would like to look at. But I guess before I go on, the concentrations that I pointed out, these concentrations just right here are about 10 to the 24 centimeters. So that's just that yellow dot, right? The yellow line right there. So there are hundreds of such things just in this image, and many more that are not there. And this is what, if you zoomed in on one of those objects, that's what it would look like. There would be 1,000 galaxies essentially orbiting around, all held together by gravity, not just their mutual gravity, but the remaining mass that we call dark matter. So these are massive systems whose mass is of order 1 billion times the mass of our sun. The next thing is, as I say, baryons only make up a small fraction of the matter in the universe. The remaining matter is really this invisible dark matter that many of the people here are looking at and working on. It makes up 6 times as much. And if you want to imagine what this means, it is as if you were looking at a mountain chain and all you're doing is seeing the snow and the snow-covered peaks. The rest of the mountain is invisible to you. The peaks that do not have snow, you can't see. The bulk of the mountain, you cannot see. The valleys and the small hills, you cannot see. And so that's the next challenge. How do you start to map that out? So just to give you an idea, this is what our galaxy would look like. This is an artist's rendition. And it's actually exaggerated because really the proportion of our galaxy to the halo would be something of order factor of 10. But that's what it would look like. There's our galaxy in the center, and it's basically embedded in a ball of dark matter that extends out in radius by about a factor of 10. Telescopes are time machines that by looking deeper and at fainter objects that are further away, we are actually looking back in time. We're looking at a time when light left that object. So even today in the sky, if we were to look at the sun, we're actually looking at the sun as it was 8 minutes ago. And that makes for really interesting interview questions. Just as an aside, since you guys had your interviews. In this particular instance, one of the satellites known as the WMAP was measuring the afterglow of the Big Bang. And the afterglow of the Big Bang has features in it. These features were imprinted into the microwave background roughly when the universe was about 375,000 years old, or roughly 400,000 years old. The fluctuations, oops, I think we're disconnected from, I have this crazy, yeah. So
The
I am,
screen has come in between, so you just
close this.
just minimize it. That's it.
All right.
For some reason, can you unshare and
Right.
again reshare the screen?
Okay, there we go. And you want me to unshare and reshare?
Yes.
Got it?
And then, full screen?
Yes.
So the-
Great. So looking at the microwave background, we see a pattern that looks like a dipole. The dipole pattern is coming from the fact that the Earth is moving around the sun is moving around the galaxy itself is rushing to the nearest concentration. Remember, gravity is king here. So we have all this motion that ends up creating a dipole pattern in the sky, a red shifting and a blue shifting. We can take that out. When you take that out, and what this is showing are 3 satellites, successive missions with improved resolution, you can see that there is fluctuations in the microwave background. These fluctuations are really quantum remnants of quantum noise that generated during inflation period. They are quantum noise generated and then stretched to huge scales. They span the entire universe, and that noise is, as I will try and show you, responsible for all the structure that we see in the universe. You can look at the power spectrum of that of the fluctuations, and with Planck, it's now mapped out exquisitely to small scales.
Can I ask a question again? Sure. What is the definition of quantum noise?
So it's just what is the so if you have an oscillator, right, in a quantum system, it's in an uncertain state. It's constantly at the 0 point energy is 1/2 h. And so there is a fluctuation going on in the very fabric of space-time. And that fabric of space-time is being imprinted as it's generated, the fabric is being expanded and it gets frozen in. So it's frozen in as a wave. That wave then carries with it information, gravity, and draws in matter. And so you have fluctuations both in the matter field and in the photon field. We are seeing that fluctuation in the photon field. And people can actually calculate what the power spectrum should come out if you were doing, certain models of the simplest models of theory. And the power spectrum comes out about right. If you look at these fluctuations these peaks, the first peak, the second peak, the third peak, and you try and understand what's controlling them, their positions, as well as their amplitudes, it turns out that they are affected by cosmological parameters, they're affected by astrophysics. But if you make certain simplifying assumptions, you can start to get a handle on the very important and fundamental cosmological parameters. What do I mean by that? You can start to understand whether the universe is flat or if it's curved on the global scale. You can start to understand whether the universe, what the matter content of the universe is. You can start to understand what the baryon fraction in the universe is. So this curve up here is moving up and down. It's changing the matter content of the universe. And you can see that as the matter content goes up and down, the relative heights of the different peaks changes. Similarly, if I hold everything else fixed and I change the baryon fraction or the baryon content of the universe, the peaks also change, but they change differently. And so with this kind of variations and understanding how these variations are playing out, one can start to fit and try and understand what the parameters are that govern the large-scale structure of space-time in our universe. Now, mind you, you have to be careful that there are way too many parameters, and one has to make some constraints. One has to add some constraints, and I'll point out what those constraints are. But nonetheless, we can start to get handled. And what we get is the fact that numbers for the matter density in the universe, or the Hubble constant, or the age of the universe particularly. Remember, in the start, I told you that in the mid-'80s, we had an idea, we couldn't pin down the age of the universe better than factor of 3, from 7 to 20. Now, we can basically say it's 13.8 plus or minus what? Like 0.15 or something like that. It's incredibly precise now, and cosmology is moving into the arena of precision. There are people here working on some of this stuff and looking forward to Euclid mission that's supposed to go up, measuring some of this to even higher precision, down to 1% precision. So we are now in that situation. The amplitude of the power spectrum has been very well constrained. The Hubble constant, okay, we'll come back to the Hubble constant. The matter content of the universe has been very well constrained. The shape of space-time is now known to be flat. We know that we had dark energy. I told you about that. We have ordinary matter, which I've already discussed. And then all of a sudden we discover that in addition to ordinary matter and this mysterious dark matter, which at least we can understand as matter, there is this dark energy that we really don't understand. And the first, sort of the only way to think about it at this point is Einstein's cosmological constant, the cosmological constant that Einstein introduced in order to try and construct a static universe. What he called his mistake is, in fact, not a mistake. The universe has manifested. Yeah.
Sorry, this picture of your universe mass composition.
Yeah.
How do you get these numbers like 0.03% of heavy elements and things like that?
These
As a
things?
quantification, yeah. How do you get
So in the first instance, microwave background tells us what the total matter content is. And you can tell what the total baryon content is. Okay. Now the question is, how do you break this down? I've sort of swept that under the rug. You can do Big Bang nucleosynthesis. So if the universe is born with certain number of protons and photons and electrons, then you can evolve that hot universe. It's expanding very fast, and at some point it's cooling down. The particles themselves are being separated, and early on it's hot, it's dense, and you can get nuclear reactions going on. So you can fuse the protons into deuterium, and then into ultimately into helium, and then lithium. But as it's expanding, the density is going down and the temperature is cooling off, and you cannot do the nuclear reactions anymore efficiently. And so at some point it freezes out. So the abundance of deuterium or lithium from primordial Big Bang freezes out. So you can measure that. And when you measure that, you have an idea of what the early density used to be. Yeah. Stars, of course, we can measure directly through telescopes. Okay. Now, just to you know, in the interest of being honest, we made, you know, all of that analysis that I've given you, I've just shown you, requires making some assumptions. I'm not going to go into what assumptions need to be made. They're sort of reasonable assumptions, but you always want to test your assumptions. And in addition to the assumptions, there's still some degeneracies. So I mentioned the Hubble parameter, and here are some of these correlations between different parameters. So here's the dark energy parameter. Here's the baryon content, the dark energy versus the total matter content. And you can see that as I change the value of the Hubble parameter within the scope of the microwave background, I can be moving up and down this banana. And so there is a degeneracy. You want to break this degeneracy. And you want to break the other degeneracies as well, the assumptions that you made, so you can test the models. And one of the ways to do that is to study structure at low redshifts. You can look at the fluctuations in the large-scale distribution of galaxies. You can look at clusters of galaxies. And you can use clusters of galaxies as a probe of cosmology, partly because clusters are the youngest and the most massive of the gravitationally bound systems that we have. And so over the span of 4, 5, 7 billion years, you can actually see the change in the population. By looking at how rapidly that population is changing, you get a handle on the cosmological parameters. By looking at the shape of the mass distribution, how many clusters are there per unit mass, you can get a handle on the cosmological parameters. And so, interestingly enough, the constraints that come from clusters run orthogonal to the microwave background. And so the intersection of these two is the region where you really want to sit. That reduces your uncertainty. And so using clusters allows you to do many things, including trying to understand what the dark energy is. One of the sort of simplifying assumptions that has been made so far is that the dark energy is essentially like cosmological constant, and therefore its equation of state, P over rho, is equal to -1. Okay, but we'd really like to know whether it's -1 or is it some function of time. And this is the kind of thing that the study of clusters plus the other probes of cosmology, like supernova, like the fluctuations in the galaxy population, known as the BAOs, and all of these things together will give us a way to break these degeneracies. Now, as I said, clusters are important, and let me just quickly flash up that in order to address the cosmology part of it, one of the biggest problems with clusters of galaxies is that you want to know mass, but you can't get a handle on mass because mass is mostly made up of dark matter. So the question is, how can you take an observable like X-ray or light coming out of a cluster of galaxies and figure out based on that how heavy that cluster is? And the biggest challenge with clusters is when this analysis was done with clusters discovered by Planck, they had to make an assumption about how some of these mass quantities, the observable, what's known as the mass observable, how they relate to each other. And it turns out that the reasonable assumption that they made gave a value that contradicted, that ran in tension with the microwave background result, suggesting that there is a problem here. One way to resolve that problem was to actually go and do the calibration firsthand. And so we did that. We had a collaboration of 3 of us. It was known as the Canadian Cluster Comparison Project. Here's our logo. CCCP is our title. And our motto was, it's good for the masses. Now, as I say this, I notice that nobody here, it doesn't make sense to this population here. But you know what I mean. CCCP, and it's good for the masses. Oh. Right. So I think I'm the last generation who remembers the Cold War. Yeah, so you guys are too young. CCCP is the old name for Russia, and Russia was communist, and communism's great motto was, we are doing things for the masses. So we are doing things for the masses too. Clusters of galaxy masses. Anyways, yeah, I think that's what it is. Anyways, you guys, it's okay. We had fun when we came up with all this, but we did do good science, and we were able to show that the calibration that was assumed is actually robust, and because of that, there really was a tension, which eventually led to the micro background people reevaluating their analysis, and some of the numbers changed. Now this difference is 1 sigma, and things are sort of closer in agreement than they used to be. That's a talk for cosmology. How did we do it? What was involved? I can talk about that the next time I come. I'm going to shift to the astrophysics part of it. Now, how much time do I have? 4:40. Okay, that's good. All right, so I told you that this is the initial condition. We have fluctuation spectrum in the mass density field across the entire universe. But what we want to know is, how do we go from this to this? These are galaxies. Or to this. These are clusters of galaxies. Or to this. This is the large-scale structure of the universe. This is how galaxies are distributed across the universe. So how do we start from something that's absolutely smooth with fluctuations, ripples literally, that are 1 part in 100,000? That's about the size of your hair floating on an ocean, to structures that look like this. And I've already told you this, that we have only 1 experiment. We cannot repeat this or alter conditions. But there's another problem that I haven't told you about, that when you start thinking about the physics that goes into the formation of galaxies or structures bigger than galaxies, the scale of the physics itself spans at least 10 to the 15 orders of magnitude. We're talking about diffusion all the way up to tidal fields that stretch out over 200 megaparsecs in scale. All right. So we're looking at systems that are incredibly complex, span an incredible range, incredible dynamic range. And at the best we can do today, with the state-of-the-art computations, the best we can do is 10 to the 5, maybe 10 to the 6. And in some instances, we can push it to 10 to the 7. So we have about 8 orders of magnitude still to go. So here, I told you in the beginning that theorists had to be creative. We still have to be very creative in how we go about doing this. The way we approach the problem is through numerical simulations. I mentioned that with the emergence of high performance computing and increasingly greater and greater computing power, it has now become possible to do this. So I'm going to show you side by side a movie where dark matter only, no baryons so far, dark matter only is being evolved. This is a run that we did in 1998, just the beginnings of the computational game. And then right next to it, you will see something that is emerging today, a current simulation. So let's do that. There we go. So this is today. This is structure that's being lit up from the bottom, and you're seeing more and more of it. And you can see how fine it is. The number of particles here will dwarf this. And so you can see that the intricate filaments, the networks, the clusters that are forming at the intersections of those filaments. And in this case, at least this is a time evolution, what you see here in blue smudges are those ripples that are being laid out. So we can take the ripples from the time of decoupling and propagate them forward to whatever initial conditions we want, which is in this case, in this case, it's just dark matter. So particles that are going to interact by gravity only. We put down their distribution has been set by the ripples, the power spectrum that we know came out of the inflation, and we observe it in a microwave background. It's been moved because we can't go back to the microwave background. We cannot start there. We can only start at some intermediate. This is no hydro. This is just pure gravity right now. Yeah, pure gravity. This would be, collisionless evolution involving just gravity. We're not doing, I'll get to hydro. And here, what we're seeing is that just these ripples in the matter distribution are such that they will evolve into the kinds of structures we see today. The phrase, that we sort of came up with, and I'm sure others have come up with, is that gravity is a genuine capitalist system. I told you about communism, now I tell you about capitalism. All right. The rich get richer. Why? Because gravity, where there's higher density, will draw in more and get richer. And so structures form where things are already privileged. And voids form where things are underprivileged. Yes. Okay.
Just click on this.
I can't see it.
Yeah, over here.
Okay. So I click
Just
on
click
that.
Yeah, now you can close this. Just close this. That's it. Now it should.
Okay. There you go. Okay.
It should be on.
Okay. So now what happened? Oh, it's fine. Okay, it's fine. Okay, so I'm going to zoom in on one of those nodes to show you how local structures are starting to form. And the idea you want to keep in mind is this, that in this kind of power spectrum that we've laid down, where gravity is building up things, the shape of the power spectrum is such that small structures form first, and then they merge together to form successively larger systems. So there's a hierarchy here, and there's a hierarchical merging going on, and you will see it in a second. So let's take a look at that. There we go. So this is the same sphere. It's expanding with the universe right now. So everything is separating. But at some point, mutual gravity starts to pull things back. And now you see little things that have formed are falling in to form a slightly larger system. So that's a group of galaxies now. That's another group of galaxies. These two will merge over time. We make a bigger halo that effectively is a cluster of galaxies. And you see all the satellites that are orbiting around, and the central object has formed now. And, so this is known as hierarchical clustering. This is an outcome of the nature of the power spectrum that we put in, plus gravity. And so this is how structure is forming from just pure dark matter. But of course, we're not interested in just pure dark matter. We're interested in baryons because we observe baryons. But before we do that, we can at least look at some global statistics and ask the question, is the universe that we have created on the large scale similar to the kind of universe we have today? You can plot up the mass functions of these systems, of the halos, bound gravitational halos that I showed in the movie. And you can see that there is a match with the observations. On the other hand, if you take something like a single halo and look at all the satellite galaxies inside that, and you do this in a cluster of galaxies and you plot it up, so the line here is the simulation and the dots, the circles, are observations from the Virgo cluster. You see for the largest systems, they look pretty good. But when you do this for the Milky Way, something's going wrong. You should not expect that much of a deficit. So that means two things. Either the model is wrong or we're missing objects. In other words, some of the objects are so small and faint that we haven't seen them. At least we hadn't seen them when this plot was made. There are many more of these objects that have been discovered since. So this curve has gone up, but it hasn't gone up all the way. And the question is why? Well, why goes back to this issue of baryons. We see stars. So we have to go back and understand how stars form inside these halos. And then what is the physics that governs these stars? So I'll skip over that. And so if you put in baryons, then you got to start worrying about a whole host of physics. First of all, gas is collisional. So you have to start modeling them using hydro. So fluid mechanics, in addition to that, you have self-gravity, you have dark matter gravity that is influencing the fluid, you have cosmic expansion that's influencing the fluid dynamics, you have shocks, you have compressional heating, you have turbulence, thermal conduction, viscosity, so on and so forth. Then on top of that, gas cools. As gas cools, it will settle down at the center of the potential. And when it does that, it becomes like a dense cloud of gas. It is unstable to fragmentation, and it will start forming stars. That's where your galaxies start forming. So pooling leads to galaxies. In addition, you have some debris of gas that's left over, which becomes part of the circumgalactic medium. It is essentially a blanket that sits around the galaxy. It too has structure in it and can form all sorts of multi-phase clouds in it, hot clouds, cool clouds, which you can now observe. And then you have stars in the galaxy. You have supermassive black holes that have formed in the galaxy. Occasionally, the gas will fall into a supermassive black hole and it will burp. And it will release a huge amount of energy. And as it does that, that energy, in fact, impacts a huge part of its environment. We call that AGN feedback, or when it happens with stars, we call it stellar feedback. But essentially, this is like the gas around the galaxy is constantly going through this heating and cooling cycles. It's being heated by this AGN feedback. It puffs up, then it cools. Some of it trickles back in, feeds the black hole, and again, you have a burst. And so you have a constant cycle of heating and cooling cycles going on. Of course, stars have their own dynamics. We treat stars as collisionless particles, so they're only responding to gravity. But then there is also black holes, and black holes are collisionless, but they also suffer dynamical friction. So as they move against the background of dark matter and baryons, they lose their velocity, but in effect, they're losing angular momentum. And so they spiral in, and they come into the center of the galaxy, and they end up sitting there. Now, if you have a merger, like the mergers I showed you, you'll have two systems bringing in black holes. These black holes will orbit, and finally, at some instance, will merge. So then people like Shuhadip can go and measure their signature. So there'll be, you could in principle use these systems to start to predict the gravitational wave background. You have, as I mentioned, feedback. And feedback has an effect that you do. You heat the gas, you ionize the gas. When you ionize the gas, you quench the galaxies. You stop star formation temporarily because you've run out of fuel. Then the gas cools, comes back in, star formation picks up. So the heating and cooling cycles also lead to cycles in star formation or inflow of fluids. And then there's other stuff that we're not even starting to think about, at least in our simulations, other people are, radiation, we treat it in the most minimalist way possible. We assume that the whole simulation is optically thin, but it's not. Then you have dust, you have magnetic fields, you have cosmic rays, and a whole plethora of physical processes that we have just swept under the rug because it's way too complicated to try and get a handle on those. So I'm not going to go through this, but some of this tells you, well, I will go through it very quickly because I want to highlight this. So some of it you can do direct, you use discrete hydro codes that evolve hydrodynamics. There are two types. There's the smooth particle hydro, there's the adaptive grid methods, and now more recently there is a combined that takes advantage of the benefits of both. So these are the hybrid schemes, but essentially you are evolving fluid equations directly. Now the next thing is you have direct calculation of the cooling and the pooling, but we don't know how stars form. You give me a dense cloud of gas and ask me, how do stars form in this? What is the mechanism and what is the star formation rate? We have no idea. The theory of star formation is still very much in its infancy. There is very active work going on. People like Yves Ostreicher are busy trying to solve this problem, but it's a tough nut to crack. And so as far as we are concerned, we have to do something simplistic. We observe in the universe that whenever you have a certain amount of density, there is a certain amount of star formation going there. We just plunk that from observations, that empirical relationship, and we put it in here. So that's sort of a bias because really we want to do this, from a theoretical perspective. We also have no idea how radiation flow, feedback operates because we can't resolve it. It happens on scales so far below our resolution that we cannot do it. So we have to put in models to actually try and capture these behaviors. The key thing here is that some things we do directly, some things we do through subgrid models. Some of the subgrid models are basically processes we know, and others we are completely clueless about. These are what Donald Rumsfeld would have called the unknown unknowns. Right? And unknown unknowns are managed by some free parameters, which is very unsettling for a theorist. But nonetheless, that's where we are. So this is an example of one of these simulations. You have a structure forming, you have galaxies forming along the filaments, different regions of the universe are being lit up, you have explosions going on, and you have gas being ejected, which is feedback going on. And you can look at this. This is the simulation that we've been studying. I'm not going to go through the details of this simulation. If you're interested, I'm happy to share this with you. And then if you happen to be at Harvard or a collaboration of Harvard, Max Planck, and one other place, MIT, and you have tons of money and you can pay people to create beautiful movies for you, this is what you get. This is a movie made by the illustrious team that's based at those three institutions. Look at the networks that are formed. In fact, this was an IMAX movie. So this is a dome IMAX movie that's being shown here. You have explosions going on. You have gas that's being ejected. This is known as the baryon cycles. The gas is ejected. Eventually, it will flow back in. You have galaxies are receiving gas. They're forming stars. You see them as blue. When they shut down and cannot form stars because the gas around them is too hot, they turn red because the star cellular population, once it can't form stars, it's aging. The aging leads to reddish, red colors. It moves the stars towards the cooler part of the spectrum. And, this is essentially how the universe is thought to evolve. Eventually, all of the universe gets filled up with hot gas. And the hot gases are coming out of galaxies. So basically what we have here is free parameters that I told you about. We can make pretty, movies. The question is, how do we settle what those free parameters are? And the way we do it is by looking at observations. We have to go back to some observations as constraints. So we have galaxy stellar mass function. This is what the number density of galaxies per unit mass in stars, which we can observe looks like. And we can generate that from the models and tune it so that it comes out about right. We can also take the stellar density, the number density of stars going back in time, and ask the same thing, that let's tune those other parameters to get this thing right. In other words, we're trying to use the most minimal amount of observational constraints we need in order to tune as many parameters as we can. And then hopefully the model being consistent from that point on will allow us to make predictions. So other people use slightly different metrics to tune their simulations. The bottom line is we're using today's metrics, things that we see in the sky today. We compare them so that we get the right number of galaxies coming out. Sorry? These exponents? Well, they are related to the power spectrum of the dark matter. In dark matter, the exponent is -2, but for baryons, it's not, because what's happened, as I show you, well, I can show you later, but what happens is in the smallest galaxies, so on this side of the mass function, the smallest galaxies are very fragile. As soon as the stars blow up, their potential well is not deep enough to contain that gas. And so the gas is ejected and the galaxies stop forming stars. And so the number of galaxies that you see is actually much shallower, flatter than the number of halos that you see. This actually explains why in Milky Way we do not see enough satellites. So satellites really only formed a few, those halos only formed a few stars before they were shut down. Okay. At the high mass end, we have the same problem. The high mass function for the dark matter basically goes like this. We see a very sharp turnoff in the galaxy population. And now we know that that's the black holes. Black holes are starting to pump energy in and are shutting down these things. So we're running out of time, right? Bulges and things like that, or the disks of star formation going on. Now we're starting to get into a regime where we can start to do interesting physics or interesting tests with these models, but there's always this niggling feeling, are we getting the models right in the first instance? And the way to do that is to test it in a regime where it was never tuned for. So we tuned it primarily in this region right here. And what I'm going to just very quickly show you what happens if I try and test it over here. And some things were surprising to us. First thing is that the morphology of the galaxy actually was surprising to us. You see, by mythology, conventional mythology, we expected all the galaxies in massive halos to look like this, red balls of stars. Turns out some of them are star-forming disks. We did not expect that. And when we looked at this much closer, it turns out that actually nature does just that. there are a fraction of objects that have gas that are forming stars. And when you look at the fraction as a function of mass, you find that lower mass groups preferentially have star-forming disk-like galaxies in their center, and then the high mass systems have these kinds of systems. So we actually discovered or rediscovered something that nature had already imprinted, but because of the way we observe and look at galaxy populations in a slightly biased way, we had missed it. It may have been known at one time, but over time, people filtered their samples down, and today the samples that you have tend to be biased. And so that's an important thing to be concerned about. So I'm going to skip this. We have been looking at these galaxies and looking how many stars they form versus their stellar mass. And what you will find up here, if you look at it, is that our galaxies tend to be sitting up here, where bulk of the observations are down here. In other words, our systems are fine on the low mass end, but as we move up to higher and higher masses, our galaxies are starting to form a little too many stars, too fast. And other people have their own problems. Like, for example, if you look at the Simba shows that 90% or 100% of the galaxy should be down there, which is also not true. Observations show that it's really about 70 to 75%. 75% down here, 25% up here. What does it mean to be down here? It means you're in a state where you cannot form stars. The black holes have shut down star formation. Up here, the galaxies are forming stars. So this is that cycle of heating and cooling. We are not getting the cycle right, but neither is anybody else. That is one of the opportunities. I could call it a failure, but if you're a graduate student in the audience and you go to conferences and you hear talks where people say, we have solved the galaxy formation problem, it's great, look, I can show you pretty pictures. I'm telling you, lift the hood, kick the tires, and see where it leaks. This is where it leaks. You can fix this. This is your job now, right? These are some of the exciting problems that you can make your mark on. So, this is something that you should be aware of. And let me just finish off by a very quick summary of where I've just ended up. I've shown you that over the past 30 years, physical cosmology and the study of large-scale structure and the study of the universe and the evolution of structure itself has gone from literally being a happy fictionalized story-making process to something that is now being overwhelmed by data. We are so tightly constrained that we are now struggling with the models. The models can't keep up. For Milky Way-like systems and smaller, the models that I've presented and the others that are out there, like I've shown you TNG, I've shown you Romulus, the others are Eagle and Simba and a few others, they can make these galaxies more or less right. And they can explain the features in these galaxies, and they can explain how these galaxies formed. The problem is when you start to stress test these models to a regime that they haven't been tuned in, which is basically more massive systems that I call galaxy groups. These are aggregate, gravitationally bound systems of roughly about 4 to 10 galaxies, not the hundreds, not the thousands so far. Let's set that aside. Let's just move one step over and ask if we get those systems right. And what we find there is that the galaxies do well in the beginning, but as you go up the mass scale, they are starting to show signs of strain. And what is the sign of strain? The black hole model, this unknown that I mentioned, where you are trying to model the behavior of a black hole, both the input of the gas and the output of energy. Our models are rather simplistic, and we're seeing the effects of that. And so that's where the opportunities are. How do you model AGN feedback correctly, or at least physically reasonably, in a system like what I've just shown you, where we still do not have the dynamic range? You need to come up with a physical model of the system that we can plug in here and then see if those models work in a reasonable fashion. So Suwadip was mentioning that, the way to make progress is to do multi-layered simulations. You have very fine but limited range simulations. Then you have very big cosmological simulations. Saurabh, we were talking about something very similar. You run these very high resolution simulations of star clusters. We can't even resolve a star cluster here. But we can tell you what the tidal fields that would act on a star cluster would be. We can tell you what the accretion history of a star cluster would be. Combining these two kinds of processes can lead to progress. And that really is the way forward. So ultimately, we want these models to be holistic. Galaxies are the building blocks of everything. Galaxies impact their environment. You cannot just say, I've got my galaxies right, now I can go home. Because if those galaxies are impacting the groups, and we can observe those groups, and the groups are not realistic, sorry, the job's not done. So let me stop right here. The environment is observable. We have to get the galaxies and the environment right. So this is what I mean by the next frontier is the holistic modeling. Okay, thank you very much.
Thank you, Arif. That was wonderful. So questions? Yes, sure.
At the high mass end, you mentioned that this is probably related to the AGN feedback.
Yes.
Do we have a sense yet what about the AGN feedback? Is it we are feeding the black holes too much? As a result, it's burping a little too much, or the burp is fine, but the coupling of the burping energy and the ambient gas or gas in the environment, that is wrong. Like, do we have a sense of what we need to tweak?
Yeah, so the answer is yes, but let me clarify. Here's what I was trying to show you. So this black line is the dark matter halo. The dots here are galaxies. You can see that at the low mass end, they're flattened. That's a stellar feedback. And the high mass end, they're steepened. That's AGN feedback. Now, you've asked exactly the right question. So the way it's modeled into these simulations is that they try and couple the inflow of the gas to energy. How much energy is coming out? The simplest models, most of these models are very simplistic. They say we will extract 10% of m dot c squared. So 10% of the rest mass of the energy that's coming in. But the amount of energy that's coming in, the model for that is kind of simplistic in itself. And then there are free parameters in this model. So how do you tune those free parameters? You tune it so that you get this steepness. It turns out that the way the energy is being put in on the galactic scale, it's actually burping way too much. But at galaxy scales, it doesn't matter. It doesn't matter because this is what happens when you run it on the galaxy scale. This is an image of a burping of a black hole on a galaxy. What's happening. So galaxy is right there, the orange sort of disk sitting there. The black hole burps, and it ejects this energy fluid, winds, out of the system. It doesn't actually impact the galaxy. What it does is it impacts the surroundings of the galaxy and prevents all the gas that's sitting out here from going into the galaxy. That's how the galaxy shuts down. I can do this in many different ways. I can shoot out gentle streams of energy. I can shoot out huge, powerful bursts. I can blow a bomb and heat the gas up. So there's multiple ways of doing it. The models that people have settled on really are like the bombs. They go off, or we're very powerful jets that get ejected. And nobody has asked the question, what impact is this having on its environment? This is the part that I didn't show you, that if you looked at this in the environmental sense, you find that this is sort of it's the logarithm of the thermodynamic entropy. So this sort of entropy proxy of the hot gas has a very flat plateau, and then sort of drops very steeply. And you can see all of them have this. They have a very flat plateau, and then they sort of drop. This flat plateau is not observed. Observations show a power low, which means in this system, what's happened is that AGN has burped tremendously, shot all its energy out here, and superheated the gas. So the thing that we're working on right now is to see, can we add that as a constraint, that I want the entropy profile of the surrounding gas to be reasonable? And can we get a model that is able to do that and get the galaxies right at the same time? And so that is one of the challenges. And it involves, solving this problem involves trying to model the black hole a little bit more realistically as well.
So some of my cosmologist friends tell me that the small number of satellites around Milky Way is a problem, and they need to invoke something like interacting dark matter and so on to solve this. What you said some time back seemed to suggest that the instability of small galaxies might actually be a solution to this. Is that what you want to suggest?
So I think if I was giving a technical talk, the rigorous answer would be, before I jump to interacting dark matter, I want to understand how baryons are behaving in the first instance. And yes, we know that baryons are doing this. I mean, this plot that I showed you just a little while ago, where the baryons are, the galaxies are flattened, whereas the dark matter goes up. That is something that happens. This is, work that has been known. So we need to take that into account before, and then ask, how much of a deficit do we still have? And the answer at this point is that between the combination of the two, between the discovery of new satellites around M31, the Andromeda galaxy, our neighbor, and the Milky Way now, with Gaia coming online and all of that, giving data, we are discovering more and more very faint systems. So the plot is starting to fill in. And at the same time, the theory plot is starting to come down because we have baryon processes being included. So I'm not convinced at this point that there is still a very large discrepancy. So that's where things stand right now. Now, I may eat my words next year, but at this point in time, that's the way the trend seems to be.
So these are extremely expensive simulations. And when you want to just tweak one of these parameters so how do you deal with it? So I also have to suffer through this, not at your level, but to some level. But how do you deal with this? Do you have like low resolution simulations that can guide you some way?
Yes. Yeah, that's exactly what we do. My graduate student should really be busy right as we speak. It's morning there, or coming up to, doing exactly that, doing low resolution simulations. So I want to run them at 10 to the 5, but we have to start by 10 to the 7 or 10 to the 7 is where we're running right now. And the volumes are much smaller. So 25 megaparsecs, 10 to the 7. That can be run on our supercomputers in 2 or 3 days. So they run 2 or 3 days, we'll get a parameter, then becomes tricky. Once we have a set of parameters good, there is a lot of degeneracy here. So it's not clear that there's a unique solution. We have to actually increase the resolution and try again. Now we'll take 30 days. galaxy and saw all sorts of clouds of gas. We had nothing like that in our simulations. Now we get to 10 to the 5, and we can start to see the beginnings of these clouds starting to form. But at the same time, other people have done just idealized simulations of asking the question, what happens if I successively increase the resolution? Do I find a point where it sort of converges? And the answer is, at this point, no. Those simulations would have to run down to a parsec scale before they'll converge. There's no way. This is not in my lifetime. Okay, in my lifetime, that ain't gonna happen. So then we have to come up with some clever way of saying, well, there's turbulent diffusion, there's conduction, we have to wave our hands really hard and sort of erase those structures at some level. But if I was selling you my models, I'd tell you how great it is. If I'm opening the hood and letting you see inside, then, I have to tell you, there's an oil leak here.
When I was seeing, whenever you see these beautiful pictures, lots of grains and stuff like that, and you also see them in several other contexts. You were mentioning networks of a different type.
Yes.
So do we ask the same questions about scales at which things are maybe ordered beyond you can't make out? I mean, is there some notion of scale? Can I relate that to a bacteria colony, for example, on a lab slide?
I haven't thought about
complexity.
I haven't thought about bacteria colonies. I have thought about neurons because my wife is a neuroscientist.
That's fine.
And the problem here is that we haven't concentrated our attention on the filamentary structure in the large scale structure. So what I mean by that is, I don't know if anybody who has applied network or graph theory to these things to calculate whether this is, on some scale, is it a scale invariant network or is it a small world network shifting to, a different type of network on larger. What we do know is that on sufficiently large scale, it does become homogeneous and isotropic. That much we know. So, if you average over a sufficiently large region, then it is a homogeneous and isotropic universe, and then we can all breathe a sigh of relief because our calculations are all based on that simplistic notion. All right, and it satisfies the Copernican principle. But on small scales, yeah, there are these filaments, there are structures, and filaments themselves are evolving. I couldn't show you this, but when you were doing this early on, you have small filaments. At the nodules, you have galaxies. Then as time goes on, the galaxy will fall into a cluster, so it'll become a big blob. These filaments will merge together to form a much longer and bigger filament. So filaments themselves are growing hierarchically. Void networks are growing hierarchically. The whole system is growing hierarchically. What I can't answer for you is there a description of this, because I haven't seen it, but it's an interesting question.
Yeah, maybe a comment on this is we slowly going towards not only calculating the power spectrum, but also going at the small scales and calculating high order statistics, 3-point function and 4-point function. So that kinds of bridges this two, in the sense of you can ask the data and ask at the very, very small scales, what kind of fluctuations do you see? How Gaussian they are or how not Gaussian they are. And that's possibly a place where I could actually start looking into different feedback models as physical formation.
Yeah.
Okay. Thank you, Shubhadeep. Thank you, Arif, for a wonderful colloquium. And we were absolutely I think everybody felt connected, even if they are not from the field. So thank you for doing that. And I would like to thank everyone from joining from Zoom. I don't think there is any question from the Zoom audience. So I'll conclude the colloquium, and let's give a big round of applause once again. And let's join for some snacks and tea outside.
Yeah, thank you very much.
Huh? Right. Okay.